Okay, our next speaker is Robert W. Smith, Professor of History in the Department of History and Classics at the University of Alberta. Received his PhD from the University of Cambridge in '79 and was a member of the staff of the Smithsonian Institution, National Air and Space Museum from '82 to '98. He's the author of The Expanding Universe, Astronomy's Great Debate, 1900-1931, nearly covering a bit more than what we're talking about today, and the Space Telescope, study of NASA science, technology, and politics. And it's already been mentioned that he has co-authored a rather well-known paper with Helga Craig from 2003. So, Robert, tell us all about V.M. Slipher and his mastery of the spectrograph.
So first of all, I'm pleased to say that in the book I wrote on the history of the Hubble Space Telescope that Mike just mentioned, Bill Putnam does appear lobbying Eddie Bowman. So what am I going to be doing this morning? These are the main aims that I have in this talk. I'm going to try to recover what I call here the context for V.M. Slipher's research on the spiral nebulae and the radial velocities. What I'm trying to do here is look at exactly what it was that Slipher was doing, why he was doing it, when he did it, as opposed to saying, okay, here's the important finds that emerged, where did they come from, and follow a linear line back, which I think is a misleading way to do business. In particular, I want to look at Slipher's pursuit of credibility, because the main context I'm focusing in on is Slipher as a Lowell Observatory astronomer, and that's crucial in a number of respects. It's crucial because there are issues of credibility for anybody associated with Percival Lowell in the eyes of other professional astronomers in the first decade or so of the 20th century. And then I'm also going to try and address this question, why 1912? Why is it in 1912 that he first makes these successful measurements of the radial velocities of spiral nebulae? So that's where I'm going. But first, it's poetry time, you'll be pleased to know. A glowing mist through realms of space unbounded whirls on its way by starry hosts surrounded. Dim is its luster as compared with theirs, and more the look of stars dissolved it wears. Volumes of heat from its prodigious source, to endless space it never ceasing pours. Formless and void it seems, and yet it holds a coming world within its folds. A sun lies spread within its depths and heights. Planets are there, and all their satellites. But still as yet they lie confused and blent, like starry dust lost in the firmament. Have some old burnt-out stars, once big and bright, recovered by collisions, heat and light. Well, so begins Henry R. Knight's remarkable rhyming poem, Nebula to Man, published in 1905. It's 220 pages long. You'll be pleased to know I don't have time to read all of it this morning, but it concerns an evolutionary journey from a nebula to lower life forms. This is the frontispiece to the book. So you can see the nebula, and those of you near the front anyway may be able to see some of the lower life forms in play here. The nebula through the lower life forms to man. Now, why am I showing you this? It's because Percival Lowell was an evolutionist. He sought to explain the origins and evolution of the Earth in terms of the nebula hypothesis, and the starting point for Knight's grand evolutionary poem is the nebula and the nebula hypothesis. The road to Slipher's results on the spiral nebulae start within the nebula hypothesis. It does not start within debates about island universes, galaxies, and so on. And it's Lowell's interest in the nebular hypothesis that's absolutely central, as I say, bringing Slipher to the problem of the redshifts. Now, Lowell had been a wholehearted supporter of the nebular hypothesis since at least 1876, because that's when he wrote a disquisition on the nebular hypothesis for his Harvard graduation. Although he did read Laplace on the nebular hypothesis, Lowell relied much more on the version published by Herbert Spencer. And there's Lowell with Herbert Spencer, of course, on the right. And in the second half of the 19th century, if you'd have asked someone certainly in the United States or Britain, who is the most important evolutionist, more likely than not, they would have said Herbert Spencer and not Charles Darwin, because Charles Darwin had proposed a failed theory called evolution by natural selection, because natural selection was almost dead and buried by 1900, only to be resurrected later. So, Lowell is reading Spencer. When in 1894, Lowell addressed the Boston Scientific Society and he spoke in public for the first time about the goals of his new observatory, he emphasized that the main object of study was the solar system. Moreover, and this is Lowell, if the nebular hypothesis be correct, and there is good reason at present for believing in its general truth, then to develop life more or less distantly resembling our own must be the destiny of every member of the solar family which is not prevented by purely physical conditions. So, as Lowell embarked on the search for life on Mars, it was with the conviction, derived in good measure from his belief in the nebular hypothesis, that evolution would lead to conditions on other planets favorable to the development of intelligent life. But for Lowell, it was not just from nebula to man, it was also nebula to Martian. But the nebular hypothesis came under increasing attack in the late 19th century and early 20th century, most notably in the United States from the Chamberlain-Moulton hypothesis. And that was first publicly advanced in 1904. Now, Chamberlain and Moulton were responding in part to the remarkable photographs that had been taken at the Lick Observatory by James Keeler. Here's Keeler with the famous 36-inch Crossley reflector at Lick. And instead of just tens of spiral nebulae, there's that sort of number discovered with the famous Leviathan of Parsonstown in the middle of the 19th century. Keeler reckoned that there were well over 100,000 nebulae, most of them he believed spirals, visible to the Crossley reflector. Now, drawing on these images, Chamberlain and Moulton argued for the origin of planetary systems from spiral nebulae, and they proposed that an encounter between two stars might have liberated material out of which the solar system was formed. Here's an example of one of the spirals as photographed by Keeler. Given momentum by the encounter, particles would be attracted to each other and thus accrete to form the future planets and satellites in the solar system. So for Lowell, the Chamberlain-Moulton hypothesis posed a direct threat to his ideas of life on Mars because it took no account of extraterrestrial life. So between 1903 and 1909, Lowell both engaged with the Chamberlain-Moulton hypothesis and also set about trying to revive and save the nebular hypothesis. And it's part of this process that leads Lowell to enlist the efforts of V.M. Slipher, because in 1906, Lowell set Slipher the task of examining the spectra of spiral nebulae. In particular, he asked Slipher to investigate if the spectra of the outer regions of spiral nebulae was similar to those of the outer planets. The faintness of the spirals led Slipher to be pessimistic about his chances for success, and certainly few spectrographic observations have been made of spirals before this time. Instead, astrophysicists have tended to prefer to examine the spectra of the brighter stars rather than the much more challenging nebulae. So let me just pause briefly for a moment to remind you of some points, in fact, it turns out that Bill Putnam made, and that's that Slipher had joined the Lowell Observatory in 1901 after his degree at Indiana, but he had had no advanced training in spectroscopy, spectroscopic theory, the use of large telescopes or large spectrographs. He was really, when he arrived, learning by doing, as Bill mentioned, some correspondence with Brashear, also correspondence with W. Campbell at Lick. But in large degree, it was cut and try. So this is the spectrograph that Percival Lowell ordered from Brashear, and it will end up, of course, on the back of the 24-inch reflector. This is from a paper in the Astrophysical Journal where V.M. Slipher describes a spectrograph in detail. And in part, he's doing this, I believe, because one of the key tasks he takes on is to establish credibility. This point I mentioned at the start, you've got, if you're a Lowell astronomer, to demonstrate that you have credible instruments, your researches are credible, you're not making incredible claims like Lowell and the canals on Mars. So, Slipher sets to work with the spectrograph, and what Lowell wants from him is the rotation period of Venus. That's why he purchased the spectrograph in the first place. And this was an important problem for Percival Lowell. And it's important because, as Lowell says, on the answer to it, and this is Lowell, turns our whole knowledge of the planet's physical conditions. More than this, it adds something which must be reckoned with in the framing of any cosmogony. So, again, an important point here is Slipher is attacking specific problems. And this is a Lowell style, in fact, and this is something that distinguishes the Lowell Observatory from, for example, Lick, which is much more of what's been termed a radial velocity factory, where it's a production of lots of data. At Lowell, the way of doing business is to attack specific problems and to keep hammering away at those problems, ideally until you've got the answer. Okay, so it's a quite different way of approach from some other observatories. Now, Lowell had pressed Brashear to produce the best spectrograph that he could, and the deal was for a custom-built instrument to be designed in collaboration with its eventual user. And the starting point for the design of the Lowell spectrograph was a spectrograph that had been built for Lick, the Mills spectrograph, and its main user was this man on the right, W. Campbell. So, in building the spectrograph for Lowell, Brashear contacted the users of his different spectrographs and asked for their advice on possible improvements that might be made with them. And when the Mills spectrograph itself also first went into operation, Campbell had big problems getting it to work effectively, and that would be exactly the same for Slipher and the spectrograph at Lowell. Getting these large spectrographs to function effectively was a challenge for anybody, not just Slipher in the early 20th century. Now, Slipher's degree at Indiana, as I mentioned, had given him no advanced training in spectroscopy. He was not getting any sort of advanced training in the latest kind of physics either. And so it's hardly surprising that we find him struggling when he first arrives in 1901, 1902, and as Bill mentioned, at one point, Slipher asked to go to Lick to see how the Lick astronomers employ the Mills spectrograph, and of course, as Bill mentioned, Lowell scotched that idea because of the notoriously bad relationship between Lick and Lowell. But by the summer of 1902, things were getting better. Slipher had secured spectrograms of Jupiter and Saturn that pleased Lowell, and soon thereafter Slipher confirmed the well-established rotation periods for Jupiter, Saturn, and Mars. And he also soon delivered the goods, at least from Percival Lowell's perspective, he delivered the goods on the rotation of Venus. And that's a chart of Venus by Lowell, 1906. And, sorry, 1896, I'm sorry, 1896. That's a chart by Lowell. And within a few months of starting in on the Venus problem, in fact, Slipher had evidence from the inclination of the planet's spectral lines that Lowell seized on as conclusively supporting a slow rotation for the planet that justified Lowell's claim, based on his observations of these spokes, that Venus rotated only once in each orbit. Now, Lowell's chief concern was, of course, the solar system, but this didn't mean that Slipher could use the telescope and the spectrograph at other times when there were no pressing planetary problems to address. So to give one example, Slipher participated in a program of observations of the so-called standard velocity stars. These were stars that were being observed for radial velocity at a range of different observatories. And again, it's a means for Slipher to establish his credibility. His results are matching the results found at other observatories. And that's one of the papers that Slipher writes. And observations of standard velocity stars with the Lowell spectrograph, that's 1905. He also decides through this particular investigation that in fact his spectrograph could be improved. And this, I think, is an important step on his road towards full mastery of the spectrograph. He's now making innovations and changes, trying to bring extra performance out of the instrument. It's not just a question anymore of getting the instrument to function, but improving it, developing it. And from 1910, he was also helped in that by a full-time employee at the observatory, somebody called Stanley Symes. So, as he puts it in this paper, 1905, the full power of the spectrograph has not been realized, and the agreement of the velocities from different lines of the same plate is not so close as it should be with a spectrograph of this size. So, as I say, he sets off to make improvements. Now, a very major prize for Lowell was the demonstration of water vapor in the atmosphere of Mars, which was certainly to be expected if there are canals on the surface of Mars. The fierce dispute between Slipher and Campbell over the amount of water vapor has been examined elsewhere, and particularly by David Dvorkin and also Don Osterbock, who says that in this controversy, Slipher was, in his words, ambushed by Campbell, and I think that's a correct reading. And we can ask David more about this particular controversy as David's here, but the key point at this stage is this really, I think, makes Slipher controversy averse even more. I think even before this big battle over the water vapor on Mars, he'd been very hesitant to get into any kinds of controversies. But this just reinforces that tendency. And so most of his papers later are very terse. They're short observational descriptions that it's really hard to argue with. You know, here's the position of this spectral line, and he's very hesitant to offer interpretations. And I think that's a result of this controversy with Campbell. Now, in the same year that the controversy over the Martian water vapor erupted, and that's 1909, Slipher turned again to the spectra of the spiral nebulae. Remember, Lowell had asked him in 1906 to examine the spectra of spiral nebulae, but he now turns in 1909 more seriously to the problem. And he experiments with various changes in the spectrograph. he writes to other astrophysicists for advice for how could I address this particular problem. And by November 1910, Slipher had convinced himself that the key to obtaining useful spectra of spirals was the speed of the spectrograph's camera lens. So that's, he sees that as a really key point for him. By this point, he'd also shifted from a 3-prism train to a single prism. And again, let me mention the importance of having Stanley Sykes, an assistant of the observatory, to help him make these kinds of innovations. Now, the next month, December 1910, Slipher reported to Lowell that he'd found features in the spectrum of the Andromeda Nebula that had not been commented on by earlier researchers. Although he was busy with other work for Lowell in 1911 and 1912, Slipher was still experimenting with spectra of the Andromeda Nebula. By September 1912, the spectrograph was equipped with a very fast, commercially available camera lens that Slipher reckoned meant the latest version of the spectrograph was about 200 times faster than the usual 3-prism arrangement. So on the 17th of September, and I guess that's why we're here, the 17th of September, he takes a 6-hour exposure of the Andromeda Nebula. And there was enough detail on that plate for him now to contemplate measuring the nebula's radial velocity. When he reported this result to Lowell, he was also actually quite careful not to raise Lowell's hopes too high, because this would be a very major prize indeed to establish the radial velocity of the spiral nebula. As Campbell, the Lick director, had put it in lectures at Yale in 1910, and this is Campbell, there is certainly no more pressing need at present than for a greatly increased number of nebula radial velocities. And at this point, nobody had measured the radial velocity of a single spiral nebula. So this was really a prize worth winning. Following the September the 17th plate, Slipher took another 2 plates, November the 15th and 16th, and December the 3rd and 4th. The spectra were still very faint, but Slipher thought there was more detail than on the September the 17th plate. And again, there was more detail in Slipher's view of more details on the spectra than other observers had seen before. December the 28th was the first night of a crucial 3-night exposure on the nebula. And after examining the resulting plate, Slipher wrote to Lowell, the velocity bids to come out unusually high. When Slipher measured the 4 plates, he arrived at the completely unexpected answer that the Andromeda Nebula was speeding towards the Earth at about 300 kilometers a second. And that was the fastest speed then recorded for any astronomical object. The fact that astrophysicists expected nebulae to have low velocities, comparable to and perhaps somewhat lower than the stars, speeds at most of a few tens of kilometers per second, made the finding even more striking. This then was an extraordinary result, but was it to be trusted? And so we're back to this issue again of credibility. Slipher remeasured the plates and even sent a copy of one of the spectrograms to Campbell at Lick. Slipher now reported the results to Lowell, who replied, "It looks as if you've made a great discovery. Try some other spiral nebulae for confirmation." So again, we see Lowell pressing Slipher on. It's not that Lowell is some absent director sitting in Boston. Lowell is directing Slipher. His one-time teacher, astronomy teacher at Indiana, John A. Miller, told him in June 1913, "It looks to me as though you've made a contribution that is as significant as the one that Kepler made, but in an entirely different way." So that was June 1913. But Campbell, of course, was still skeptical, because this is one spiral. And Campbell, for those of you at the back might not be able to read this, tells him this result is surprising in the extreme. I suppose, he goes on, the dispersion must have been very low, the error must be very large, I presume you've got more than one plate, and of course the ever careful, slow Slipher did have more than one plate. But Campbell was skeptical. Now, by the time we get to the American Astronomical Society meeting in 1914, and I'm sorry this is not a great image, Slipher had followed Lowell's direction and he had results for 15 spirals, some of which displayed even larger spectral shifts than the Andromeda Nebula, mostly to the red. And of course, this is a famous image because here we have Edwin Hubble and Slipher's off in the back, as always. Where is this meeting? Evanston. Yeah. Now, one of the spirals, in fact, had a radial velocity of 1,100 kilometers per second at this point, which was a really astonishing number. As I say, 300 had seemed to astronomers as absolutely baffling, but here's a spiral nebula moving at 1,100 kilometers per second. And Slipher, though, was still not prepared in 1914 to argue that the spiral nebulae are external galaxies. He'd come to the Andromeda Nebula in 1906, viewing it like just about everybody else, as a solar system in formation. And this is a famous image. This is from 1888. It was shown at the Royal Astronomical Society by Isaac Roberts, and the report of the meeting says there are ejaculations of the nebular hypothesis made visible when this was shown. Because this obviously shows a solar system in formation with planets being born. So that's 1888, 1906. Slipher's attacking the Andromeda Nebula with this sort of notion in mind. And in late 1912, Slipher had also observed the spectrum of the nebula in the Pleiades. He didn't find evidence of the spectrum of a typical gaseous nebulae, not the usual bright line. Rather, he concluded the Pleiades nebula shines by reflected light. This itself was a major find, and there's a nice quotation from Otto Struve, a very major astronomer in the 1930s, talking about how important this find of a reflection nebula by Slipher was. And this is all happening at the end of 1912, so this must surely be the most creative and successful period in Slipher's astronomical career. Furthermore, this observation of the nebula in the Pleiades, Slipher said, suggested to me, and this is Slipher, that the Andromeda Nebula and similar spiral nebulae might consist of a central star enveloped and beclouded by fragmentary and disintegrated matter which shines by light supplied by the central sun. This conception is in keeping with spectrograms of the Andromeda Nebula made here and with Bolin's value for its parallax. And he's quoting a result from 1907 by the Swedish astronomer Carl Bolin, and Bolin's answer for the parallax of the Andromeda Nebula was 19 light years. So we are here in Flagstaff celebrating the 100th anniversary of the discovery of the radial velocity of a star surrounded by fragmented matter. Are we not? Yes. So we have to be careful, we have to avoid thinking ourselves forward in time to a time when it's obvious that these are the radial velocities of external galaxies, because in 1912 they are definitely not. So shortly after, he went a bit further, in fact, in talking about the radial velocity of the Andromeda Nebula. He referred to the famous nova that had flared in the Andromeda Nebula in 1885. And so now, he says, my results on the radial velocity of the Andromeda Nebula suggest that the nebula, in its swift flight through space, might have encountered a dark star, thus giving rise to the peculiar nova that appeared near the nucleus of the nebula in 1885. And if you remember, or you've not managed to expunge the memory of Knight's rhyming poem, Knight talks about the nebula hypothesis and a collision with a dark star as well. Now, other astronomers were much quicker than Slipher to exploit the radial velocity measurements in support of the theory of spirals as external galaxies. So in 1940, for example, Engineer Hertzsprung of Hertzsprung-Russell fame said, "Congratulations," and he said, "Your beautiful discovery," that's Hertzsprung's term, "your beautiful discovery of the great radial velocities of some spiral nebulae seem to show, to me with great certainty, that the spirals do not belong to the system of the Milky Way. They are external galaxies." The radial velocities of the spirals were also central to a surprise maybe, W. Campbell's advocacy of the island universe theory in a lengthy paper in Science in 1916. Here's Campbell, and now, in this really important paper, I think, he's showing one of Slipher's spectrograms of the Andromeda Nebula. So the relationship, which I think Campbell very clearly had in mind in sometimes providing advice to Slipher, of master and pupil, perhaps we've reached a point where the pupil has outmastered the master. In the same year, 1916, a number of astronomers also used Slipher's radial velocities to calculate the motion of the Sun with respect to the system of spiral nebulae. Just as astronomers calculated the drift of the Sun from the motions of the nearby stars, so from the motions of the spirals, the drift of the galaxy could be detected. And Slipher himself performed this calculation in 1917, by which time he measured the radial velocities for 25 spirals. And he'd also switched, a little bit tentatively, but I think it's clear he switched, to seeing the spirals as external galaxies. And in the longest paper he ever wrote on his radial velocity work, and then it was only 7 pages, he explicitly argued against a general scattering of spirals. The radial velocities of the spirals, Slipher wrote, and these are his words, calls to mind the radial velocities of the stars, which in the sky about Orion are receding, and in the opposite part of the sky are approaching. This arrangement of the star velocities is due to the motion of the solar system with respect to the stars. So Slipher, in 1917, is interpreting the preponderance of redshifts as a consequence of a drift of the galactic system with respect to the system of the spirals. And so we have the galaxy moving with respect to a drift of spirals. This is not any idea of a scattering, okay? And as I say, he explicitly says it's not some sort of a scattering. Now, to underline how unexpected these kinds of numbers were for the radial velocity of the spirals, this is from a paper by the famous Dutch astronomer J.C. Kapteyn in 1910, where he was looking at the radial velocities of a number of stars and their spectral classes, as well as looking at the motion of the planetary nebulae, Orion Nebula, and here is the radial velocity. So the Orion, at that point, was measured at 0.1 kilometers per second. The planetary nebulae seemed to be moving as a group the fastest, 28.6 kilometers per second. Stars in the spectral class A to A5 were 12.6 kilometers per second. So the fact that you've got the spirals moving, some of them well over 1,000 kilometers a second, as I say, was quite extraordinary. Amongst his last publications, if you can call this a publication, on the spirals, was a short report on a spiral moving, NGC 584, moving at the fastest speed that had then been detected. And Slipher uses that to argue that, in fact, it's many millions of light years away. So this is 1921. This is before One is seen as the confirmation of the extragalactic nature of the spirals by Hubble with his Cepheid observations in 1923 and 1924. But by this point, Slipher has stopped writing papers on the radial velocities of the spirals. So when in 1923, the great English astrophysicist who Matthew Stanley will be telling us about later, wrote his book, The Mathematical Theory of Relativity, he wanted the latest results from Slipher, and Slipher wrote and sent them to him. But Slipher doesn't publish them himself. So the list is in Eddington's book, and those are the results that Slipher had secured by 1923. But that's pretty much the end of the work on the radial velocities. Essentially, he'd been left behind by the lack of instrumental capability. So he's out of the hunt for radial velocities, but he's also out of the mainstream by the 20s, because there's a new way of doing business for astronomers. They start to look at relationships between, or possible relationships between, the radial velocities and other factors like, for example, distance. And there are a range of studies. This is one of the plots by the Swedish astronomer Lundmark. There are a number of these, and in fact, studies of these go back to the 1960s when John North wrote a very important book called The Measure of the Universe, where he looked at these different kinds of plots, discussions on the nature of the de Sitter universe, and I guess we're going to be hearing more about the de Sitter universe shortly. But this is a Lundmark plot, velocity against distance. This is the globular clusters. Here's another plot by Lundmark. Now we've got distance against velocity. And whose velocities are they? Slipher, because hardly anybody else has got any. And is that a straight line? So in 1924.
There's no line. He doesn't plot.
Right. Yeah, so I mean, that's the plot, right? That's 1920. There are others, by, for example, Wirtz, Silverstein. So there are a number of people working on this in the 1920s. So this is a new direction. It's not just finding radial velocities, but it's trying to correlate radial velocities with other things, like distance. So, and there's another such effort, which is, I'm sure, familiar to everybody. It's Hubble, 1929. De Sitter, 1930. You know, I'm going very quickly through these because we're going to be getting to these in other talks in the meeting. And there's 1931, Hubble and Hummerson. And this ends the debate. Is there a relationship between redshifts and distances? And after 1931, in this particular plot, it's over. The debate is over. The 1920 plot, there was a debate. And of course, when we read the velocity-distance relation, because it's Hubble, it should always be read as apparent velocity, not actual velocity. And one thing, as a kind of coda, I wanted to mention is that Slipher initially had wondered, well, these amazing spectral shifts, are they really Doppler shifts? And so he'd been puzzled for a time. But he could think of no other reason for the spectral shift, so he stuck with Doppler shifts. Hubble, of course, never liked the explanation of Doppler shifts. And in fact, on a visit to Slipher in 1925, he came through Flagstaff with his wife and sister. They went to the observatory, and Hubble wrote to Slipher to talk about the possible interpretation of redshifts. And let me just read this paragraph, because it underlines this point that Hubble does not really think we're dealing with Doppler shifts here. This is 1925, so well before the first Hubble redshift distance relationship paper. So Hubble, there are many things to talk over. Among them, a wild idea on the variable k term for the spirals. We would call the k term now the Hubble constant, as a particular shift depending on the concentration of mass around the nucleus, which varies as the globular nebula expands into the open spirals as per Jeans's theory. And Jeans, he's referring to here James Jeans, who was extremely influential for him. Have you noticed suggestions of a correlation between velocity and resolvability or age, or something of the sort? It's vague, but very tantalizing. And I wish we could get into a time machine and go back to 1925 and hear Hubble talking with Slipher on what these things actually mean. So the conclusion, well, my main point has been to understand what Slipher was doing with the radial velocities of the spiral nebulae, at least to begin with. We really have to see him as a Lowell astronomer. And I think it's probably fair to say that while Percival Lowell was the despair of many professional astronomers, the most scientifically productive period of Slipher's scientific life was really the decade after 1906, between 1906 and 1916, when he mastered the spectrograph. Percival Lowell was still alive and pushing him and cajoling him to get the spectrograph to function on a range of different problems. So I think he was inspired and pressed. Slipher was inspired and pressed by the Boston Patricia. He had state-of-the-art instruments at a very good site. He could compete with other astronomers in other locations, and he racked up a string of first-rate achievements. But for a range of reasons that I think Joe Ten will be talking about in his paper on Slipher tomorrow, things changed very much in the second half of Slipher's career. And I've probably overrun my time by some margin.
And tomorrow morning I'll talk from an astronomer's point of view about the nebular spectrograph development that Dr. Slipher was involved in. And it's very interesting that there was another gentleman who Slipher corresponded with who got his PhD degree at Lick Observatory, whose name was Edward Pfaff. And he was also developing nebular spectrographs in that era, and it's likely that Slipher's development of the spectrograph was done somewhat in conjunction with Edward Pfaff. But on another topic...
Yeah, can I just mention Pfaff is important because, in fact, before Slipher gets his 1912 measurements of the Andromeda Nebula, he gets a very high number for a globular cluster.
Yes.
But he doesn't believe it.
Yes.
You know, we should get this number, this is wrong.
Sure.
So,
but another on that same subject, just as a preview tomorrow, Pfaff was actually the first to clearly resolve the absorption line spectra of a number of spirals before Slipher had done it. But that's for tomorrow. The one thing that I'd like to comment about also is I also saw that 1921 New York Times article where Vesta Slipher is interviewed about the distance to the nebulae. And a key point in that article, I think, is that even Slipher is quoted in there, mentions a new view of the age of the Earth. That is, your interpretation as to how far away these nebulae are is a direct function of how old you think the universe is. And people in that era, geologists in particular, had set a relatively low age for the universe. And in about 1921, radiocarbon dating was being developed, and the age of the Earth was, for the universe, you might say, was extended from maybe 200 to 400 million years out to 1 billion or 2 billion years. And it's a matter of considering the velocity of those nebulae in the context of the age of the universe that allows you to estimate how far out they are. And Slipher was aware of that clearly from this 1921 New York Times article. And even when he discovered them, the velocities in 1913, 1915, he couldn't conclude necessarily that they were at great distances because the age of the universe wasn't so confidently known.
but at that point he didn't think that they were external galaxies, so that calculation doesn't.
It feeds in to the art, what you think the age of the universe is.
It'll come to play much later with the expanded universe. Matt.
I was very interested to hear you talk about all the correspondence that Slipher did when he was trying to figure out how to use the spectroscope, because it's notoriously difficult to talk about precise operation of an instrument just in words. So I'm going to go talk a little bit about what those letters looked like, and did they actually help Slipher in the end?
Whether they helped him or not, it's just hard to say from the historical record. There are a number of other people in the room who've also looked at some of this correspondence, and they may have their ideas. But I think he's got the spectrograph pretty much in operation by the middle of 1902, so it's about a year. And which seems really quite surprisingly fast, just given the fact, I believe the biggest telescope he'd ever used when he was at Indiana was a 4.5-inch reflector. And here he is with the Clark telescope for a start. Then you've got to attach the Clark, the spectrograph to the Clark and get it to function. But he is corresponding, he's also corresponding with Brashear. And I think Brashear is clearly a very important figure, because Brashear was not somebody who built the instrument, sent it off and forgot about it. As I say, when he was designing the spectrograph for the Lowell Observatory, he consulted with the people he'd sold spectrographs to and asked them for their advice on how could he make improvements on it. So I now forget most of the details about the correspondence. Really, I think my own sense is it's Brashear who is the key figure in terms of providing advice. I don't know if you have any thoughts, Joe.
Thank you for your talk. I'm glad you brought this Eddington's table. Would you please return to it? I have a question about it. You might answer. Yes. Eddington says there are 41 galaxies coming from Slipher, but first two, 221 and 224 and GC, might be the same because all parameters are very close. So what do we know now? Are they the same?
Yeah.
M31 and M32.
Yeah, they're the companions.
Companions, but not identical.
There's another question in the back. Richard.
So I'm trying to understand, presumably Lowell was very proud of this achievement. I'm trying to understand whether, what happened at this point to make Slipher move away from this area. You didn't talk about the connection between this discovery and Lowell's enthusiasm.
Well, Lowell dies in 1916.
So is that part of the reason?
And no, he was, as I say, very supportive. This stuff is bad, as it turns out, for the Chamberlain-Moulton hypothesis, which is good for the nebular hypothesis as he's revived it, which is good for him, right? But after 1916, and this, in fact, is discussed. The best discussion of this appears in the book that Bill Putnam edited, the Centennial History of the Observatory. There was a big fight with Mrs. Lowell that went on for about a decade. And so you would say, well, why doesn't Slipher now, having established things, get a new instrument? Why don't they get new telescopes? Their instrumental capability, compared to other astronomers in, say, 1906, is very good. But by 1916 and then certainly 1926, they've been left way behind. But a large part of it is the internal history of the observatory, where a large chunk of the endowment was eaten up by this legal fight with Mrs. Lowell. And it's not surprising that this observatory staff also started to hedge against this legal fight with Mrs. Lowell. So Bill mentioned some of VM Slipher's business interests. Well, he developed some of those, as I say, I think it's pretty clear, as a hedge against something bad happening with Mrs. Lowell, trying to extract lots of funding out. And so I think by the early 20s, he basically just ran out of spirals that he could attack fundamentally.
Cormac, we'll have to take a break.
topic. Thanks very much. Superb talk. And there's one point that I always want to bring out because it strikes me the most.
Louder, please.
Just one point I want to make is not only does Slipher make an observation, but he also suggests an interpretation that turns out to be the right interpretation. And you know that bit, as you said, he was in a way it's almost the only thing he could think of. But you did such a wonderful job of putting everything in scientific context. My question on that is that he's just looking at the radial velocity of stars as suggested by Campbell, and the logical thing is that, or is there anything more to that? You know, how does he arrive at that interpretation?
You mean the Doppler shift?
Yeah, well, I mean, he's looking at Doppler shifts, but for me it's always to interpret the Doppler shift as a definite radial velocity. That's quite a brave step, as you know, for something that he thinks
Right.
of.
Yeah, I think, for example, if you read through Campbell's book on stellar motions, which is based on the lectures he gave at Yale in 1910, there's a discussion there of something that's called the K term, which is introduced to take out effects in the atmospheres of certain classes of stars. And so these were being measured as radial velocities, but Campbell had introduced this K term to deal with what he thought was a systematic effect. So always in the mind of people, I think, after this, if you're a spectroscopist, is, okay, is it really a Doppler shift or are there some other terms we have to take into account here? Is there something systematic to do with the working of the star, for example, that might be affecting the radial velocity?
Okay, thank you again, Robert.